Hello everyone, welcome to Statistical Foundation for Big Data Analysis. In this module also we continue with our discussion on principal component analysis. Unlike last module when we focused mostly on the principal components of the underlying population, here we discuss the principal components that one can observe from the collected sample. Now, if you think for a second, in statistics we basically try to predict the population based on the sample. So, it makes sense to try to observe in the same logic as the previous module to look for the maximum variability directions in the observed sample. Now, principal component is a dimension reduction technique. So, often we may have no idea about the underlying population and we may have to do dimension reduction based on the sample only, and that is why the sample principal components become extremely relevant. So, here is our p dimensional data x1, x2, xn. So, you have an n set of n data points observed from some p dimensional distribution. The sample mean, as we have talked, is just you add the values and divide by the number of observations, and we take this sample variance covariance matrix, we take the unbiased version of it. We discussed what is a sample variance covariance matrix for p dimensional data. You observe the ith component of each data point kind of is the representative of the ith dimension, and now when you are looking for the covariance between ith and jth random variables in the population, you sort of view this ith dimensions and jth dimension as the data of those two random variables, and you measure this sample covariance based on that. So, what we are doing is your basically xk, you write it as x k1 x k p. So, the ijth entry of sigma the sample covariance between ith and jth dimensions. So, here that is between x1 I xn I and x1 j and xn j, and in this case we take that to be, which is 1 over n minus 1 summation x k I minus x bar I, the mean. So, x bar I, let us say for now let us define that as k running from 1 to n, x k I, x k j minus x bar j. So, we take the unbiased version of sample variance covariance matrix. So, we take this unbiased version of it, that is we take this as n minus 1. Now, once you convert this into vector form, this is just for each dimension, this becomes this matrix. And I am not getting into details of all these matrix calculation at this moment, because we have seen this on various previous modules. So, basically what we do in sample principal component analysis, we instead of looking for the principal components of the sigma, that is the population variance covariance matrix, we actually do the look for the maximum variance directions of sigma hat, the maximum variance is present in sigma hat. And sample PCA basically analyzes the variability present in the finite data set with the hope that this is a decent representation of the population principal components, and the underlying estimation is if the sample is representative, nice representative sample of the population, whatever the phenomenon present in the sample moments and sample variabilities, that will reflect those of the population, and eventually if the sample is large enough, it will more or less be close to the population. So, this is, and with this philosophy, which is which has been invoked repeatedly all along in our study of statistics, we will apply that philosophy here also in our study of sample principal components as empirical estimates of population principal components. So, basically the goal is that, like sample PCA6 orthogonal linear combination of the variables to capture the largest possible sample variance using the sample variance covariance matrix sigma hat. And the theory part, the constructions are pretty much identical to what happens in population PCA. You just replace the population variance covariance matrix by sample variance covariance matrix. This is also a symmetric positive definite matrix, and whenever you are taking symmetric positive definite matrix, you can diagonalize, you can order the eigenvalues in decreasing order, all the eigenvalues will be non-negative, you can look for the corresponding unit eigenvectors, they are going to give you the directions of sample principal components. So, let us just quickly get into this. So, you first of all using the same philosophy, you center the observations. So, you subtract the sample mean from each of the data point, you basically replace the xi's by zi's, these are your new data points, and sample principal components will simply be certain, you will simply find certain qk, the kth sample principal component will be a direction, and you will do a change of variable towards that direction. You will basically choose a new coordinate system, which will be first of all orthogonal, probabilistically orthogonal, such that these new variables will be uncorrelated to each other, and the first first sample principal component will have the maximum variance amongst all the principal components, second principal component will have the maximum variance amongst everything except the first one, and so on. So, just like what we were doing in case of population principal components, we do the same for sample principal components, except the only exception is that, like, we replace the population variance covariance matrix by sample variance covariance matrix. So, we will see that the variance, I mean, we know this is the way, because of y hat, and shifting does not really change the variance. I mean, the variance covariance matrix of zi is nothing but variance covariance matrix of xi's, because after all the mean of these zi's are 0, and basically if you write it down, the variance covariance matrix of zi's will just, so variance covariance matrix of this data, variance covariance matrix of z1 zn is also sigma, one can check. So, now because z hat is, because as yk I is qk transpose Z I variance of y k I hat is nothing but q k transpose sigma hat q k. So, this is basically finding variance using this variance covariance matrix is something that we have used quite frequently in some last lectures. So, that we basically apply the same thing, and this will come out to be kth eigenvalue, or rather kth largest eigenvalue, so to say. This will turn out to be kth largest eigenvalue of sigma hat. So, this is what we are basically heading towards, just the repetition of same logic as in case of population principal components. So, variance covariance of y k will be just q k transpose sigma hat q k, and the covariance between y I and y j will be 0. I mean, we will choose basically q i's and q j's to be orthogonal. So, this sigma hat q j, and these are actually going to be the eigenvectors corresponding to sigma. So, sigma hat q j will basically be the jth eigenvalue times q j. So, this will just become jth eigenvalue times q I transpose q j, and q I and q j will be perpendicular. So, their dot product will be 0. That is just repeating the same logic as we saw in, to some extent, great details in population principal component. So, the linear algebra that was used there is pretty much verbatim will go through in for sample principal component analysis also. So, this is the basically the same interpretation as there. So, these new vectors essentially rotate our coordinate system to a new orthogonal coordinate system, such that they are kind of there is a natural ordering. The first direction is the direction of the highest variance present in the sample, the second direction is the second highest, and so on. The last direction is the last highest direction amongst the sample variance directions, last highest among the variance directions present in the sample. And the point is that they have to be probabilistically orthogonal, that is they have to be uncorrelated directions. The original directions need not be uncorrelated to each other. So, we look for these uncorrelated directions. As I was telling you, there are some advantage of uncorrelated directions. We saw in case of multivariate normal, and due to high dimensional central limit theorem, we can assume if you are taking mean of very large IID data set, they follow certain normal distribution. And for multivariate normal, if you are doing principal components, uncorrelated will actually imply independent, and the distribution will become extremely simple, just the product of one dimensional normal distributions. So, because of this uncorrelated implying multivariate, uncorrelated implying independent for the multivariate normal setup, this choice of orthogonal coordinate system, the probabilistically orthogonal coordinate system, that is uncorrelated coordinate directions, becomes extremely helpful. So, the way we calculate the sample variance covariance matrices are exactly same as population variance covariance matrices. The first one is just the maximum amongst these values, which we actually have seen that this is just nothing but variance of q transpose z. We just maximize these z vectors. So, we essentially look for this maximum of these variances, and subject to the unit vectors. I mean, we only look for unit vectors, unit directions. We are only interested in the directions. We discussed this in case of principal components also, that the you can basically, if the variance is in a certain direction, variance is 10, you can choose a much larger vector in the same direction to scale up the variance much more. But we are not really interested in absolute value of the vector, but we are interested in the direction in which the sample variance in this case is maximum. So, to focus only on direction, we actually impose this condition that we are only doing it towards the unit direction. So, we look for the direction, unit direction towards which the variance is maximum. So, once we find this, and this is also focusing on unit direction makes it a maximization problem over a compact set, that term I used last time also when we were discussing population PCA, and this problem has actually a solution. You can actually find a specific value towards which it the maximum is achieved. So, it is not an infinite problem. So, now once you find that direction, that gives you your first PCA, first sample PCA, just like the population case. So, for the second PCA, same as first, you maximize the variance subject to, instead of one condition, two condition. Now, you impose the unit vector condition, but also impose this orthogonality condition. This direction has to be orthogonal to the first direction you have already achieved. Once you get that, you get your sample PCA, second sample PCA. You get that second maximization problem, like as we saw that this is variance, you are maximizing variance amongst all vectors, all unit vectors that are orthogonal to already obtained first PCA. This condition implies this implies this. So, orthogonality achieved. Similarly, if you keep going, at the kth step, the condition you impose, maximize variance, keep it unit vector, and pick the vector to be orthogonal to all the other directions obtained in previous k minus 1 steps. So, this way when you proceed, you get an orthogonal coordinate system of decreasing order of variance. So, each new component maximizes the sample variance under the requirement of being uncorrelated with all other previous components. Sample PCA constructs a new coordinate system aligned with the directions of maximum variability in the sample. The vectors for q1, q2, qp form an orthogonal rotation of the coordinate system. The sample PCA basically is an empirical approximation of population PCA, pretty much in the same philosophy, under which sample mean is an empirical approximation to population mean, sample variance is an empirical approximation to the population variance. Based on all these are based on, in case of PCA, based on the sample variance covariance structure, and we start with the unbiased one, not the maximum likelihood one. We start with the unbiased sample variance covariance matrix. So, population quantities are unknown. The reason why we need sample principal component analysis is that essentially statistics happens because population quantities are unknown. So, because population PCA requires the true mean and true population variance covariance matrix, in reality they will perhaps not be observed. They can even be not observable. I mean, you may not have access to anything more than one sample. I mean, in reality, one way you can get a better estimate of that, like if you can keep sampling, if you have a really huge sample, maybe then you have a kind of a, because a very large sample tends to become same as the population, maybe you can get a better idea, but often your sample will not be as large as you want. And remember, like as I was saying, sampling is the most expensive part of, often most expensive part of statistical analysis. You can 5,000, 10,000, 5 lakh, 5 crore, does not matter. What is your budget, that guarantees, that puts a constraint, not guarantee, but whatever is your budget, that puts a constraint on the sample size you work with. Sometimes not budget, sometimes you simply work with sample that has already been collected by someone else and you have no access to other sampling, for maybe not for budget constraint, for some other constraint, but whatever it may be, sample is what from which statistical analysis often starts. So, no access to population on many occasions. So, you have to do dimension reduction if needed using whatever the sample you have in your hand, hence sample PCA. So, population relations are not directly observable, they have to be interpreted. The relations in the population that you want to predict, the model. So, basically modeling is basically modeling of a relation present amongst the variables in the current distribution. Whatever you do, you have to do based on the sample present in your hand. So, sample PCA will reveal correlation between the variables that is observable in the sample, directions of the maximum variability present in the sample, with the hope that gives you directions of maximum variability in the population. It gives you potentially a dimension reduction approach. Hopefully, if the sample is representative of the population, and let us say you take first two sample principal components and they describe a big chunk of sample variance, you may hope that those two directions will also describe big chunk of population variance. So, sample variance covariance matrices are basically approximation to the population variance covariance matrices. Sample means are approximation to the population mean. So, sample PCA will be an approximation to the population PCA. Not only that, in 10th talk, the last talk of second module, if you remember, we discussed something called consistent estimator. So, just to connect the dots and like use some terminology which we use there. I mean, we did not really use consistent estimator too much after that. Just the fact that as sample size grows, sample mean converges to population mean, and sample variance covariance matrices converge to population variance covariance matrix. In fact, sample PCAs become consistent estimator of the population PCAs. So, they become same as population PCAs as sample size increases. So, in particular, this sample PCAs are extremely important when we are doing real life data analysis based on a fixed sample of very high dimension. So, sample PCA based on this observed data are basically, as we observed in case of population PCA, they will be your eigenvectors of the sample variance covariance matrices. So, when you have the unknown population structure, when you have an unknown population, because the distribution parameters are really inaccessible, sample PCA is the only thing you have to work with, and in some sense it is easy to deal with because its population by nature is unobservable. Even if it is observable, it can be infinite. The computation involved are more complex. Samples are finite. So, it is just mostly addition, subtraction, division and multiplication when you are doing calculation based on the sample. So, the calculation structure is easy. However, although it is easier to calculate things using sample, there are certain problems with sample. The sample eigenvalues are fluctuating, depends on sample. So, normalized eigenvectors in the sample will will have some differences with the population, of course, population eigenvalues, and they will be dependent on the sample. But that is the same issue with all sampling, all problems that all sample dependent problem solving approach. So, fluctuation in the sample will get reflected in the fluctuation in the sample PCS. So, you take different sample PCS, you may get different directions. So, now however, as we were discussing, like as sample size increases, sample principal components tend to become population principal component or tend to become very close to population principal components. We show this using a particular example. So, what we do, we just draw a sample of three samples, one of size 20, one of size 200, one of size 2000 from a bivariate normal distributions. Well, we know the bivariate normal distribution to begin with, it is our bivariate normal distribution. So, this this is not really what happens in real life. I am just trying to give you an example, simulated example to show you how sample PCAs behave vis-a-vis population PCAs and what happens when sample size increases. We see that as the sample size increases in this example, the sample PCAs tend to become very similar to the population PCAs. So, we have, but of course, here we know the population and we know what are the population PCAs are. We are using this known example of known population scenario just to demonstrate what happens in case of the sample. So, we choose this bivariate normal, we kept the mean 0 just to start with the centered scenario, and suppose your variance of the first one is 4, the second one is 3 and the covariance between them is 2. You can diagonalize and find the population PCA just like we did in last class, and you can generate a random sample. You can construct a sample variance covariance matrix from there and calculate the sample PCA as we were discussing today. Diagonalization will lead you to eigen decomposition both in sample PCA scenario as well as the population PCA scenario. In case of population PCA, you have to diagonalize the population variance covariance matrix, meaning this matrix. In case of sample PCA, you have to actually calculate this based on the sample and diagonalize that matrix. So, what we will do, we will just plot both population PCAs and sample PCAs on the same curve and see how it goes. So, here is what is happening. So, your population PCAs are blue lines, this is your distribution, this is your density ellipsoid of this bivariate normal. You have chosen 10 sample points from this 20 sample points from this population. The sample PCAs are these red lines, the major axis are the bigger direction of the bigger lines, in case of population PCA, the major axis of the ellipse gives you the direction of the first population PCA and the minor axis of the ellipse gives you the second population PCA. They are this light bluish, this dark blue is the density ellipsoid, this contour. The light blue is the major axis and both the light blue lines are major and minor axes of that ellipse of those population PCAs, and the red lines, perpendicular red lines are the sample PCAs based on this sample of size 20. They are close, but not almost completely aligned, and this is happening because sample size is 20. Now, let us see what happens if sample size is 200. Same colors, light blues are your population PCAs and reds are the sample PCAs. Look at this, jumping from 20 to 200, sample PCAs seem to be very close to the population PCAs. Now, go to 2000, not 20,000, just 2000, practically inseparable. Same color, population PCAs are light blue, they are just hidden somewhere here. If you look very carefully, you can still see them, but the sample PCA, the dark red color sample PCAs are almost lying on top of the population PCAs. It's happening because sample size is very large. So, sample essentially becomes population. So, sample PCAs become essentially population PCAs. So, this is the lesson, like if you basically increase the sample, as we were saying, they are consistent estimator. If you increase the sample size, sample PCAs tend to become same as the population PCAs. So, this demonstrates that like you can perhaps work with sample PCA itself if you do not have the information about the population, and you can go do the dimension reduction using sample data and sample PCA itself. So, with this motivation, we will conclude today's talk. In next class, we will actually formally derive the sample PCAs, and we will see basically they will be the eigenvectors corresponding to this sample variance covariance matrix. Thank you for now. We will see you in next class.